All right, here is the first part of our centripetal force talk. It's going to be about motion and centripetal force. Chapter is going to be put into two parts. So we'll do part one now, and then another video will be part two. Centripetal force keeps an object in circular motion. All right, which goes faster on a merry-go-round, a horse near the outside rail or one near the inside rail? While a hamster rotates its cage about an axis, does the hamster rotate or does it revolve about the same axis? We begin to answer these questions by discussing the difference between rotation and revolution. Two types of circular motion are rotation and revolution. These actually mean two different things where you might think that they're the same. An axis is the straight line at which rotation takes place. When an object turns about an internal axis, this is an axis located within the body of the object. The motion is called rotation, or spin. When an object turns about an external axis, the motion is called revolution. So if you think about it, the Earth rotates, it has a rotation of 24 hours, but it revolves around the sun, a revolution, every 365 days. So the Earth has rotation and revolution. The rotation of the Earth is every 24 hours. The revolution is 365 days. The Ferris wheel turns about an axis. The Ferris wheel rotates while the riders revolve about its axis. Oh, and here's the example that I just gave. Earth goes about both types of rotation. It revolves around the sun once every 365 and a quarter days, and it rotates about an axis every 24 hours. What are the two types of circular motion? We just talked about them. Actually, and it's not even written right up here, is it? All right, now on to rotational speed. Tangential speed depends on the rotation speed and the distance from the axis of rotation. The turntable rotates about its axis while a ladybug sitting on the edge revolves around the axis. Does that make sense? I hope it does. Which part of the turntable moves faster? The outer part where the ladybug sits or near the orange center? It depends on whether you're talking about the linear speed or the rotational speed. These are two different things. All right, the linear speed, these are the ones we've been doing problems with. Linear speed is the distance traveled per unit of time. A point on the outer edge of the turntable travels a greater distance in one rotation than a point near the center. The linear speed is greater on the outer edge of a rotating object than it is closer to the axis. The speed of something moving along a circular path can be called its tangential speed. So the velocities we've been talking about in class have been tangential speeds because the direction of the motion is always tangent to the circle. So if we talk about our circle, we're always talking about that tangential speed. Rotational speed is a little bit different. We sometimes call it angular speed. It is the number of rotations per unit of time. All parts of the rigid turntable rotate about the axis in the same amount of time. All parts have the same rate of rotation or the same number of rotations per unit of time. It is common to express rotational speed in revolutions per minute, RPMs. All parts of the turntable rotate at the same rotational speed. A part further away from the center travels a longer path in the same time and therefore has a greater tangential speed. So, rotational speed, anywhere, the rotational speed will be the same, whether you're closer or further out. Rotational speed does not change. The tangential speed increases the further from the center you go. All right. All parts of the turntable rotate at the same rotational speed. A part further away from the center travels a longer path in the same time and therefore has a greater tangential speed. That's what we talked about in A. B, a ladybug sitting twice as far from the center moves twice as fast. That way, but the rotational speed will be the same. Tangential speed and rotational speed are related. The tangential speed is directly proportional to the rotational speed and the radial distance from the axis of rotation. Rotational speed, we're not going to be calculating rotational speed very much. So we're going to disregard this for now. I want to talk about a little bit differently in class. All right. At the axis of the rotating platform, you have no tangential speed. So in the very center of the circle, when it spins around, there's no tangential speed because there's no velocity in a straight line direction. But you do have rotational speed, so if you stood in that very center spot, you would spin in a circle. You rotate in one place. As you move away from the center, your tangential speed increases while your rotational speed will stay the same. Move out twice as far from the center, you have twice the tangential speed, but you still have the same rotational speed. At an amusement park, you and a friend sit on a large rotating disc. You sit at the edge and have a rotational speed of 4 revolutions per minute and a linear speed of 6 meters per second. Your friend sits halfway to the center. What is her rotational speed? What is her linear speed? Okay, rotational speed does not change. It's going to be the same 4 revolutions per minute that you are, because that does not change. And your linear speed is going to be 3 because she is halfway. Remember, these are directly proportional. If you go in half, then it's going to be cut in half. How do the wheels of a train stay on the track? The train wheels stay on the track because the rims are slightly tapered, meaning they angle a little bit one direction. A curved path occurs when a tapered cup rolls. The wider part of the cup travels a greater distance per revolution. If you ever take old styrofoam cups, they're bigger on one end than the other, and you roll it on its side, you'll see that it curves in a circle. A tapered cup rolls in a curve because the wide part of the cup rolls faster than the narrow part. So as this cup, it will roll in a circle because of the tapering of the cup. Fasten a pair of cups together at their wider ends and roll the pair along a pair of parallel tracks. The cups will remain on the track. They will center themselves whenever they roll off center. So here's a picture of that. If you put these together, this is kind of how train tracks work. They have them tapered like this to where they will center themselves. When the pair rolls to the left of center, the wider part of the left cup rides to the left track where the narrow part of the right cup rides on the right track. This steers the pair towards the center. If it overshoots towards the right, the process repeats, this time towards the left as the wheels tend to center themselves. The wheels of railroad trains are similarly tapered. This tapered shape is essentially on the curves of railroad tracks. On any curve, the distance along the outer part is longer than the distance along the inner part. When a vehicle follows a curve, its outer wheels travel faster than its inner wheels. This is not a problem because the wheels roll independent of each other. For a train, however, pairs of wheels are firmly connected like the pair of fastened cups, so they rotate together. The tapered shape of railroad train wheels, shown exaggerated here, this is blown up pretty big, is essentially on the curves of a railroad track. So you take a look and this is how they're set. So when a train rounds a curve, the wheels have different linear speeds at the same rotation. So here we have a narrow part of left wheel goes slower, so wheels curve to the left. Then the wide part of the left wheel goes faster, so the wheels curve to the right. You see how it shifts back and forth? So train wheels ride on a pair of tracks. For straight line motion, both tracks are the same length. But which track is longer for a curve? The one on the outside or the one on the inside? The outer track is longer, just as a circle with a greater radius has a greater circumference. What is the relationship among tangential speed, rotational speed, and radial distance? Things to think about. All right, this is the end of the first part of the notes. We'll do another video for the second part.